selecting, you will always prefer customer over a peer, over a provider. This was to make money, otherwise save it, and only pay if you have to. Exporting a route had to do with how your decision about whether you advertise a prefix or a path to your other neighbors. So when you advertise it, what that means is they will send you traffic to carry to that destination. So it's the decision about, am I willing to carry that traffic? And so we said, this is the export rules. If that prefix gets advertised by a customer, I'm going to export it to everyone because I'm happy to send traffic to that customer. If it's advertised to me by a pure provider, I'm only going to export it to my customer. Again, because my customer will pay me, whereas the pure provider won't. Okay. You should be very, very comfortable with the Gao-Rexford rules. Comfortable all the way from why we have them, that this notion of how money gets exchanged, how they get implemented in the form of these export and import policies, and actually how they get exchanged when we get to how BGP actually gets implemented. Yep. Right. So, and that was when we got to attributes and how you actually do attributes. Oh, so we had, for example, the local preference. I'm getting to that in a minute, but okay, let's jump ahead. Hold on to that for a second, and we'll get to it when I put that up. So how is BGP implemented? So you should understand the role of border versus interior routers, right? And you should also understand the role of eBGP versus iBGP versus IGP. Okay, so we had this picture that looked like this, where we had border routers, or routers that connect to a router in a different AS. Interior routers, all their neighbors are within the same AS. And we said border routers will have these eBGP sessions with routers in other domains, and they will also have iBGP sessions with routers, interior routers, and all routers within an AS. Many people get confused between iBGP and IGP because we think when we look at the picture, an interior router is running an IGP protocol. It's also running or participating in this iBGP session. Important to remember, they're doing very different things. The IGP protocol, this is the intra-domain protocol, is establishing connectivity between all routers and hosts within that AS. The iBGP session is how an interior router knows how to reach destinations in a different domain. Okay? Yeah.
To send data for iBGP session, will it use IGP or is it like totally different?
It uses IGP. So it's actually running TCP on top. You mean for the iBGP sessions, right?
Yeah, like to send this information about other ASs and other routers, will it use IGP?
Yes.
Will it use the same like distance vector?
Yeah. Any other questions on this picture? Yeah.
On advertisements on eBGP, are you only advertising like the prefixes you own or also the prefixes you know how to get to?
Any prefix, this is where the import and export policy, and maybe this is also the earlier question. So if you take the black router there, it's receiving advertisements from some other AS for any prefix that AS is willing to carry traffic for. Okay, and then likewise, if I take what prefixes that router is advertising to the other AS, when I advertise a prefix, I'm telling that AS I'm willing to carry traffic to this destination. Okay. So how do we actually do this? Remember that route advertisements look like prefixes and attributes. Okay, so prefixes was what we just discussed, it's the destination prefixes. But we talked about 4 types of attributes that influence your route selection. One was the AS path, right? The other one was MED and IGP. So going back to policies, our high-level policies always we want to make or save money as per the Gao-Rexford rules. Once we're good with that, then what we do is try to select the best performing path, which is where AS path comes in. You pick the shortest AS path. And then when you're done with that, you try to optimize for your use of bandwidth. And that was the little dance between MED and IGP, okay? Which determines whether your traffic leaves, how far through your network your traffic is carried. So going back, I think, to your question now about how do I actually implement the Gao-Rexford rules. One way is in local preference. that attribute because I assign a local preference to a particular neighbor. And that tells me whether I like routes coming from that neighbor or not when I propagate that route.
All of this is about route selection.
Yes.
And what about route export?
So there you have a policy that decides, do I advertise this route? Is this a customer route or not? Yeah. Even local pref is hard-coded in some sense. Right. An operator goes in and configures that all routes coming in on this link have a local preference of this value. And if you look through the example we had some 300 and 100, those were manually configured by your operator. Any other questions on? Okay, so things you should know how BGP works, both at the high level. This, money follows, routing follows money notion and the GAU-Rexford rules. You should be able to apply it to different kinds of BGP topologies. You should also know how BGP actually implements all of this and how attributes like MED and IGP and AS path and all interact. Okay. You should have, at least at a high level, some sense of BGP's limitations and security issues, not expecting you to know this in any great detail, but just have a sense of, for example, BGP may not pick a path that is the most optimal in terms of path length, right? Because it's prioritizing policy over performance. So at that level, you should have a sense of BGP's limitations. Any questions here before I move on? Okay, so where are we? We went kind of bottom up. We went from links to routers to topologies, intra-domain routing, inter-domain routing, which has a very different set of concerns. It has to do with how the administrative setup of the internet and how addressing is done. And so at this point, we actually have all the pieces we need for any two hosts on the internet to communicate. Okay, so you should be able to take a picture like this and step through, where did NYU get its address from? How did NYU learn about Berkeley's address? What are Verizon and AT&T actually exchanging in terms of BGP routes? What protocols are running at different points? What does a packet header look like when the link crossing Verizon to AT&T? Does it look different going on the link between AT&T and Berkeley? The answer is no. It's kind of a trick question. You update the IP header, but it's the same IP header being carried through. Okay. You should also understand which protocols are running on different links, where eBGP is running, where iBGP is running, where IGP is running, and so on. Any questions before I move on? Yeah? Right. So, and we haven't covered Ethernet. So, we've covered learning switches and STP. You should know how learning switches and STP works. Learning switches and STP are usually applied in Ethernet networks, which are an L2 network. We haven't covered Ethernet, so we're not going to expect you to know Ethernet on the exam. That said, what is an L2 network versus L3? It's really whether you're routing on IP addresses versus some kind of lower level L2 address. That's the entire difference. And when you cross so typically an L2 network would be a particular technology like Ethernet, and it would have its own technology-specific way of doing routing. And it does have the ability, if you have a multi-hop network or graph that is made up of that same L2 technology, so typically the example is Ethernet, Ethernet at L2 should be able to carry the packet from one end to another off that local network. Yeah. Yeah. In fact, Ethernet pretty much is the only one that uses it. Yeah, you should know how STP works at the algorithmic level and how learning switches enable plug and play and how that works without worrying too much about the context in which it's being placed. But you should know the trade-offs, like STP floods or it ignores certain links. And you can know that without knowing anything about Ethernet, so that you should know. Any other questions? Okay, so backing up now, we've gone kind of very bottom up to figure out we've reviewed how all the plumbing works. Let's go now, again, top down, and we've talked about what gets implemented and how it gets implemented. We should not lose sight about why things were done a certain way, and we spent a lot of time on this in the first few lectures of this class. Come back to it after you've now understood how things work. So going way back to lecture number 1, we said the goal of the internet was to allow hosts to communicate across multiple networks. You now know how hosts communicate across multiple networks. You know about BGP, you know how money gets exchanged, you know about how addresses get configured, about where a network operator goes to get addresses, you know all of that. But come back to, what were some of the underlying design decisions and why did we like them? And make sure that you understand that now in the context of understanding how these different protocols work. Okay, so rolling back all the way to the very first lectures, we said that the internet reflects certain fundamental design choices on why it's built this particular way, and you should know those and you should be able to appreciate them. So there were 3 main ones I want to highlight. The decision to have a best effort service model. Right, that was this idea that I'm going to send a packet and I kind of hope it gets delivered. And we said even before that inherently a network is a shared resource. All of us as users are sharing the bandwidth and capacity of that network. And we said that there are 2, that was the notion of statistical multiplexing. So be comfortable with what is statistical multiplexing and why we use it. It's much more efficient than giving every user a dedicated slice of the internet. Would have never scaled and been hugely expensive. So we like statistical multiplexing and we like sharing. We talked about 2 canonical approaches to sharing. One was this notion of reservation, that a user, an end host, is going to explicitly reserve some bandwidth along a path for some duration of time. And as opposed to best effort where I just send my packet and I hope it gets through. Okay. And we talked about 2 canonical designs for implementing each of these. One was reservations implemented via this thing we said was circuit switching, and then of course best effort was packet switching. And after those first few lectures, we've only talked about packet switching because that is what the internet does. But you should remember this notion of reservations and the trade-off relative to best effort, and also at a high level the implications for implementing reservations in the way that circuit switching did. So remember this was an end host. When you want to reserve bandwidth, you set up a circuit by sending this control message through the network saying, I'd like to reserve some bandwidth. And then you get an acknowledgement saying, you're good, I've reserved some bandwidth, and then you can send traffic over that circuit until you're done with it, at which point you tear it down. Okay. That was circuit switching. Understand the trade-offs between circuit switching versus packet switching and what was the pros and cons of each approach. You're obviously not expected to know circuit switching in detail because we didn't cover it, but we covered it at enough of a level that you should be able to understand the trade-offs. Okay. Any questions on circuit versus packet switching? I know that was a while back. Yeah?
Sorry, you might have said, but both constitute statistical multiplexing, or is it only one of them?
They're both a form of sharing, so they're both a form of implement statistical multiplexing, but they do at very different granularities. Right? Circuit switching is at the granularity of a circuit. You've booked that bandwidth for the entire duration. So whether you're using it or not, that bandwidth is reserved for the duration of the reservation. Any other questions? Okay. So the second design choice that we emphasized was this notion of modularity through layering. And going back to the layers we discussed, we talked about breaking down end-to-end communication into these tasks that we then arranged or organized in these 5 layers. Okay, going from applications on the top, building on top of a reliable delivery service, on top of best effort global delivery that used best effort local delivery, all the way to actually putting bits on a wire. Okay, this was our L1 to L7. And we said that once you have these layers, we introduced this notion of protocols. This is the language by which peer layers communicate. Okay, so 2 peer layers on either end. We have protocols so that they know the syntax and semantics, they know how to understand each other. Going back to that CEOs exchanging letters example. We had this figure that is important to remember, which is that at every layer, you can have multiple protocol implementations, except at the network layer where we have one universal protocol, that's IP. Things to remember, there are 3 important properties to remember in this picture. One is that we have this notion of strict layering. So every layer builds only on the functions implemented at the layer below, and it supports the API that the layer on top builds. Okay? There was a question somewhere, yeah. Yeah, good question. Where's BGP in this picture? You got something that triggered many people with SDN. That was one of the... BGP is not here. This is the data plane layering. So this picture is captured